The final video of this week. Whew. So this is the one where we kind of put it all together and you see how we can use antiderivatives to actually evaluate definite integrals. So again, these ones are the ones that have bounds and they do mean something other than just antiderivative. They denote the area under that curve between those two bounds. So what we're going to be doing is we're going to be using the fundamental theorem of calculus part 2. So if you have the integral of f of x dx from a to b, that is capital F of b minus capital F of a, where f is any antiderivative of lowercase f. So that's saying if I took the derivative of capital F, you'd get lowercase f. So now that we know how to find antiderivatives, we can actually use this fundamental theorem of calculus to evaluate these integrals. So this is the shortcut method. Okay, so we're going to look at how we do that. So we're going to evaluate these definite integrals. So again, indefinite integrals have no bounds, they just mean the antiderivative, but definite integrals mean area under the curve. And we don't need the plus c for definite integrals. So if I integrate 10, the antiderivative of 10 is 10x. I know that I'm going to use f of x, capital F of x, to be 10x, and I need to evaluate it at 4 and at -2, and subtract those. And we have kind of fancy notation for this. We have a bar, so we've kind of used that before, evaluated at -2 to 4. So what this means is first I'm just going to plug in 4 into the function, and then I'm going to subtract off the same function plugging in 2. So this really is f of 4 minus f of -2. That's what I'm doing here. So then this is 40 plus 20, so we'll get 60. So the area under the curve 10 from -2 to 4 is 60. This is one we could have done before, but we will quickly move on, letter B, to a problem that we could not have done before with geometry. So first thing we're going to do is we're going to take the antiderivative. So this is going to be x cubed divided by 3 plus, remember this is just x to the 1/2. So this will be x to the 3/2. When I divide by 3/2, I'm going to end up flipping that fraction. It'll be 2/3. And we're going to evaluate it at 0 to 1. So we're going to plug in 1 first. So it'll be 1 over 3 plus 2 over 3. And then we're going to subtract off what we get when we plug in 0, which if we plug in 0, it's just 0. If you add this up together, you get 3 over 3, which is 1. Okay, moving right along. So secant squared theta, the antiderivative of that is going to be tangent. So this is 2 tangent of theta. We're going to evaluate it from -pi/4 to pi/4. So this is my f of b minus f of a. This is 2 tangent of pi/4 minus 2 tangent of -pi/4. Tangent of pi/4 is 1. Tangent of -pi/4 is -1. So this becomes 2 plus 2, which is 4. For letter D, this is one of the ones that I'm going to split up. This is going to be t to the -1/2 minus 1. So I split up the fraction. I'll get 1 over square root of t minus square root of t over square root of t. So that's how I get t to the -1/2 minus 1. I'm going to take the antiderivative, so this will be t. If I add 1 to the exponent, it'll be positive 1/2. When I divide by 1/2, that's going to be the same thing as multiplying by 2. And I'm going to subtract off t. evaluated from 4 to 9. So that means we're going to plug 9 in first. So this will really be 2 times the square root of 9, which is 3 minus 9. So that's my f of 9 minus 2 times the square root of 4 is 2 minus 4. So that's my f of 4. So this is just my the fundamental theorem of calculus, part 2. This is 6 minus 9 minus 0. This is negative 3. So just as a reminder, what we have just found is that the area underneath this graph from 4 to 9 is negative 3. So we're doing something quite complicated, actually. All right, the last two problems, we've got our exponential function, base e. Luckily, exponential function is the greatest, the easiest. It's just e to the x again, but from 0 to ln of 5. So we'll plug e to ln of 5 minus e 0. This will be 5 minus 1. We'll get 4. Last one, I could rewrite this as 3 integral of 1 over x from 1 to e squared times dx. So that 1 over x, remember, you cannot use the power rule with that. This is going to be ln. This is going to equal 3 times ln absolute value of x. And then that evaluated from 1 to e squared. So it's a little bizarre that we're taking our upper bound and plugging that in first. So we're plugging in e squared first. I'm dropping the absolute value signs because they're not necessary for e squared, and they're not necessary for 1 either. So remember that ln of e squared, that's just going to become 2. Ln of 1 is just 0. So that becomes 0. Whole thing becomes 6. Okay, so just with like taking derivatives, these basic antiderivative rules and evaluating these integrals will be something that you just need to get really good at. So for homework, you have a circuit that helps you practice all of this, as well as a new type of activity called a Big Ten worksheet. Both of them are self-checking, so you should be able to know whether you're getting the problems right. So I'll check that they're done on Tuesday.